So now we're going to deal with the case of shocks, shock waves in traffic. So then first of all, they're not very exciting, or not as exciting as they sound. So they're just abrupt changes in density. And I'm going to try and play this video. I don't know why, but it's something very annoying.
For the first time, Japanese researchers have conducted a real-life experiment that shows how some traffic jams appear for no apparent reason. They placed 22 vehicles on a single track and asked the drivers to cruise round at a constant speed of 30 kilometers an hour. At first, traffic moved smoothly, but soon the distance between cars...
Okay, so what's happening here? This guy appears at this point, which is really annoying. So you can see here, the shock wave is just a density of abrupt change in density of traffic. So the shock wave is propagating backwards through the traffic here. So these guys drive ahead, and you can see the thing moving back. There's an abrupt change in density. These guys suddenly drive from this low density to this high density state, and they basically come to a stop, and it propagates backwards. Let's see if we can see that.
And asked the drivers to cruise round at a constant speed of 30 kilometers an hour. At first, traffic moved smoothly, but soon the distance...
No idea where this guy comes from. All right, it's quite an interesting picture of it. It gives you an idea about shock waves and traffic. They're really just like a traffic light's actually a shock wave. Okay, so what are we going to do about these characteristics in these shock waves? What can we say about them? So let's have a look at some of this stuff here. So the first thing is, when do the shocks meet? So when do two characteristics meet? Because it doesn't necessarily happen that they meet at the same time. So what we've got here is two characteristics that meet. And it turns out that the neighbouring characteristics are going to meet. So this is at a point x0, and this is x0 plus delta x, and they meet at this point. So what are the equations of each of these curves? So remembering that this is the t-axis and this is the x-axis. So this curve is x. Well, maybe I should do this one here first. Okay, it's going to be x0 plus the density at x0, the speed of x0 times t. Okay, remember that the speed depends on the density, which depends on the initial position. And this is, so this curve here is x0 plus delta x plus c of x0 plus delta x times time. And they meet at this point here. So we basically just equate these two curves. Some time later, this is the time here which we'll call capital T. They're equal. So x0 plus c of x0 times capital T is equal to x0 plus delta x plus c of x0 plus delta x times capital T. And then we rearrange and solve for t. So what do we get? We get the x0's cancelled, and we get c of x0 plus delta x minus c of x0 must equal delta x. So we can divide by this divide by delta x. So we'll divide by delta x. This is equal to 1. Sorry, and I've got to be careful here, it's minus delta x. So divide by delta x, this becomes minus 1. So I take the limit, so I get t of c dashed of x0 is equal to minus 1. So the time is equal to minus 1 over c dashed of x0. And of course, if the derivative is always positive, then the characteristics won't meet in positive time, they'll meet negative time, they'll never meet. So the first point that happens, that is the smallest value. Okay, so I've written over here, or I shouldn't have written in the forbidden zone. So let me just, in case you can't read that, write it up here. is equal to minus 1 over c dashed of x naught. Okay? So the smallest value of minus 1 over c dashed of x naught is the first time a shock forms. And you can see in simulations that I showed you, remember that took a while for the shock to form, you can check it. Great.